the tail end of KSP kind of thing. And now we're going to jump into talking about acid equilibria. Now, the way that our textbook is set up, I think I told you, this chapter 6 is sort of a refresher in equilibrium. Chapter 7 is all about titrations. Chapter 8 is a more thorough treatment of equilibrium, which we'll talk about in a little bit. And then chapters 9 and 10 focus on acid-base equilibria and polyprotic acid-base equilibria, respectively. And so the tail end of chapter 6 talks a good bit about acid-base stuff, sort of the basics, and then some of that is repeated at the beginning of chapter 9. So I'll try to avoid duplication as much as I can, but some of this stuff is both places. I'm going to get through it. Right. So when we talk about acids and bases, there's the three definitions that you talk about in Gen Chem. There's the Arrhenius acid base, where acids donate a proton and bases donate an H+. Arrhenius definition is sort of limited. It requires that our solvent be water, and it requires that our acids all have H+, and that our bases all have OH- to begin with. Most of the acids we tend to deal with fall in that category of having an H+, but there are lots of bases that we deal with that are not anything like having an OH-, especially as we get into biochem kind of thing. Organic bases where you talk about a lone pair on a nitrogen and it's having basic properties and things like that. And so then we step up a level to Bronsted-Lowry definition of an acid and a base, where an acid is a proton donor and a base is a proton acceptor. This is a much more, this is a much broader view of acidity, and it's the one that we're going to sort of tend to stick with in this semester as well. And then if and when you take inorganic, the definition of inorganic is Lewis acids and bases, where we talk about, instead of proton donors and proton acceptors, we talk about electron pair donors for bases and electron pair acceptors for acids. And that's that works well when we talk about metals. Of course, inorganic deals a lot with metals. And so we have our Bronsted-Lowry definition of acids and bases, and that's the one that we're going to tend to stick with. When we talk about acids and bases, one term that we should mention is conjugates. And so a conjugate acid-base pair, these are compounds, species in our solution that differ only by an H+, right? They only differ by a proton. And so, examples that we might think of right off the bat, if we had a strong acid like nitric, the conjugate base would be, would not have a C in it. I don't know where that came from. The conjugate base would be NO3 minus. Another example would be NH4 plus and NH3. So conjugate acids and bases. When we talk about conjugate acids, conjugate bases, the term conjugate is always used for whatever the products are. So, for example, if we had these two reacting, so HNO3 plus NH3, these are going to react to give us NO3 minus and NH4 plus. We have our acid and our base. We don't call the reactants conjugates, right? We just call those acids or bases. And then whatever our products are, right, this is going to be our conjugate base of nitric acid, and then this is our conjugate acid of ammonia, NH3. Okay. So that's just a little bit of a refresher, hopefully, about conjugates. The other thing of interest is KW, talking about KW. And again, hopefully this was, you remembered most of this when we talked about, when you did the review. And so KW is equal to, it's a constant, it's 1.0 times 10 to the negative 14. Now, remember equilibrium constants are temperature dependent, and so this is at 25 degrees C. So it changes a little bit. But 1.0 times 10 to the negative 14, and that's equal to the concentration of H plus times the concentration of OH minus, because this is considered the autoionization of water. Where water will essentially ionize itself. And so H2O breaks into H plus and OH minus. Since water is a pure liquid, of course, he's excluded from that equilibrium expression. The ions left and have this constant ratio. Again, this is in pure water, which is not really pure most of the time. We'll talk about that a little bit later. All right. So, talking about strong acids and bases. A strong acid or a strong base, what makes it strong? It's a strong what?
pH.
So pH is most strong acids and strong bases do have either high or low pHs, far away from 7, that's true. But when we talk about a strong acid being a strong acid, what do they do that makes them strong?
Dissociate. Ionizes 100%.
Ionize, dissociate, they break apart all the way. And so we call those strong electrolytes, right, because they dissociate completely. And so strong acids and strong bases are strong electrolytes. Again, that means that they ionize or dissociate completely. There are 6 strong acids and 6 strong bases that I'm going to ask you to just know. You may remember these from Gym Chem, you may not. But these 6, you should be able to just recognize as, hey, that one's strong, or hey, that one's weak. And so for acids, they are HCl, HBr, HI, HNO3, H2SO4, and HClO4 for chloric acid. Those 6 are the 6 strong acids that we'll deal with. And then the strong bases are mostly the hydroxides of the alkali metals. And so lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide. Barium hydroxide is sometimes included on this list too, even though he's an alkaline earth rather than an alkali metal. I'm not going to include him. Instead, I want you to know that if we ever have a quaternary ammonium hydroxide, that is a super strong base. And so from organic, remember R is just a generic term meaning some carbon chain, right? It could be something as, well, actually, it could be just a hydrogen, but the longer that chain is, the more basic. And so R4NOH. So any ammonium hydroxide is going to be a strong base. the longer that carbon chain, the stronger that base is going to be. All right. Now, conversely, when we talk about weak acids and weak bases, well, if they're not strong electrolytes, they must be weak electrolytes. Okay. Which means that yes, they do dissociate some, but not completely. And that's why we have to use these equilibrium constants to tell us what those what that level of dissociation is. Now, strong acids and bases don't really have Ka values, right? But generally speaking, we talk about them having Ka or Kb values greater than 1. Right? So if you have a Ka or Kb value greater than 1, that means that the products are much, much more favored than the reactants. Right? Again, remember products on top, reactants on the bottom. And so if your numerator is large and your denominator is small, then you have a large Kb value. Now, they don't really set up an equilibrium, right? Strong acids and strong bases dissociate completely. They don't go back to being that ion pair. And so we don't really talk about them as having a Ka value. But sometimes when you look up Ka tables, you'll see that they have Kas that are sometimes written as just large or greater than 1 or infinite. Infinite's not a great one, but sometimes you see. I spoke a little bit last time about how when we write Ka, we have to, when we write KSP, we always start with the salt and we break that apart into the ions. When we write our Ka expression, that always has to be our weak acid. In this class for the next long time, we're going to abbreviate weak acid as just HA. Right? H for the proton and A for everything else. And that's going to break apart, dissociate into H plus and A minus. And KB is not just the opposite of Ka, right? That's one piece where sometimes it gets a little tricky. The definition of Kb for the same, well, we could do it for this conjugate base A minus, but I'm going to do it just for a regular old base B. It's B reacting with water in equilibrium to get B H plus, sorry, that conjugate acid, and then OH minus. For some bases, like magnesium hydroxide, for example, you'll find that they don't have Kb values, but KSP values. Because they're salts, they don't dissociate very much, and so rather than having Kb values as bases, they're not really very good bases whatsoever, and so we treat them more as insoluble salts. And so you'll see those with KSP values rather than with Kb values. If we have polyprotics, well, let's do a quick example first, then we'll talk about polyprotics. Right? So pH and pOH of a solution that's 0.387 times 10 to the negative fourth molar HCl. pH, of course, negative log of that concentration. Remember that if I start my concentration with 3 sig figs, my answer has to have 3 sig figs. And 4 things that have undergone a log, the sig figs are the number of decimal places, right? We call that the mantissa, and so the number of digits in the mantissa is the same as the number of sig figs. Now the POH, there's 2 different ways of calculating POH, right? The quick and easy way is saying, okay, if the pH scale is 14, then 14 minus pH has to equal POH, and I'm perfectly okay with that. And we end up with what? We end up with 10.588. The other way of doing it is we know that Kw is equal to the concentration of H plus times the concentration of OH minus. And so we could use Kw and the concentration of our acid to find the concentration of OH minus, take the negative log of that. A little bit more involved, but you get the same answer. Okay. Now, because this is a strong acid, that's why we can just take that acid concentration and plug it into our pH expression. Right? If it was a weak acid, we couldn't do that directly. We'd have to figure out how much of that acid had already dissociated. All right, so concentration of H plus and OH minus, if we have a solution of NaOH with a pH of 11.48, so the concentration of H plus is equal to the antilog of the pH. So 3.3 times 10 to the negative 12 molar. And again, there's 2 ways to calculate the OH minus concentration, right? You could either solve for POH and then take the antilog, or you can use Kw to get through from one to the other. So I'm going to do that way. Kw equals OH minus times H plus, which is 3.3 times 10 to the negative 12. So OH minus equals 3.0 times 10 to the negative 3. So with most of these pH problems, you can either solve it, thinking about pH as the sum of pH and POH equaling 14, which of course is pKw, or you can think about it in terms of Kw and the concentration. All right, so conjugate acid-base pairs for sulfuric acid. Well, sulfuric acid is H2SO4. What's the conjugate base for H2SO4?
HSO4 minus.
Yep, HSO4 minus. And so that still has 1 proton, and so HSO4 minus, what's his conjugate base?
SO4 2 minus.
That's it. Okay. All right, so these form an equilibrium with one another. These form an equilibrium with one another. So we have 2 Ka values, right? H2SO4 has a Ka value. HSO4 minus has a Ka value. We call this one Ka1 and this one Ka2. The 1 always goes with the stronger acid or stronger base. And so Ka1 is the first proton being removed, K2 the second proton being removed. Now, opposite that, KB1 is the first proton going back on the base. And so KB1 is connected to Ka2, and KB2 is connected to Ka1. A little confusing there, but just think about it as sort of making this cycle, right? We have to lose 2 protons to get all the way to the base, and we gain 2 protons back to get all the way to the acid. So Ka1, Ka2, then backwards Kb1, Kb2. And so if Ka2 equals 0.012, how do we find Kb1? How are those two related?
They're also related by KW.
That's right. And what operation do I need there, Meredith?
Well, Ka times Kb equals Kw, so you're gonna have to divide by Ka2.
So Ka2 times Kb1 equals Kw. And so we end up with Kb1 equaling 1 times 10 to the negative 14 divided by 0.012. So sulfate, not a great base, right? That's why it's on our list of strong acids.
Dr. Davis, for this one, sorry, there is something happening outside of my window, but also is this supposed to be KB1 equals 8.3?
Ah, yes, there should be.
Okay, I didn't know if I missed something.
Yeah. Kb1. Yep. Okay, so since we have a little introduction there to polyprotics, let's talk a little bit more about those. Okay? So polyprotic acids, some places you'll find they say polyprotic bases, right? Not all bases except, not all bases have protons, and so it gets a little funny, but you know, polyprotic bases is fine with me. Polyprotic, polybasic doesn't matter a whole lot. So, right, so these have multiple acidic hydrogens. For acids, of course, bases have multiple acceptor sites for hydrogen. And so because of that, they're going to have multiple Ka values. I'm going to take just a minute here to show that Ka times Kb really does equal Kw. So with the H2SO4 example that we just did, HSO4 minus and H plus, and then our Kb, if we're talking about the same acid or the same base, right? Our Kb H is, that's not this. HSO4 minus, remember, it has to react with water. React to form H2SO4 and OH minus. Now, if we add these two reactions up and see what their overall reaction is, right? Have an H2SO4 on the left and the right. I have a called bisulfate. I have this bisulfate on the left and the right. And so I'm left with H2O in equilibrium with H plus and OH minus. Now this first one, Ka, the second one, Kb, and this one, of course, we know is Kw. And when we add reactions together, we multiply their equilibrium constants, and so Ka1 times Kb2 equals Kw. And that's true for any conjugate acid-base pair. It doesn't have to be polyprotic. Okay, so that's the end of chapter 6. Like I said, chapter 6 was just a big review of equilibrium stuff. And so I'm going to get out of that and jump into chapter 9. Hopefully you downloaded the chapter 9 lecture notes. They were on Moodle this afternoon. And this is all about acid equilibria in a little bit more detail. Okay, so let's dive right in. So strong acids and bases, like we said, they dissociate completely. The thing to keep in mind with strong acids and strong bases is that because they dissociate completely, we assume, at least for now, we assume that the concentration of the acid equals the concentration of H+. We may discover that's not a great assumption later on, but for now, we're going to assume that's true, right? This whole chapter, both of these chapters, I'm going to talk about most things just in terms of acids, but the equal and opposite apply to bases, right? Assume the concentration of base for a strong base is equal to the concentration of OH minus. So that being said, let's do another quick example, hopefully. The pH of concentrated nitric is 15.6 molar. pH is just negative log of that concentration. We end up with a negative pH. What the what? Yes, it's possible. We get a negative pH of 1.193. We say the pH range runs from 0 to 14 just because that's where most of the concentrations lie. But of course, we can have pHs that are outside that bound. There's some super acids out there that have pHs of like negative 30, which is crazy to me. They don't actually, there are some super acids that don't have hydrogens. They're just really good at taking electrons, which is the Lewis definition. And those, it's hard to really talk about pH since there's no H+ concentration, but they have sort of a pH equivalent, and they're very, very negative, negative 30, I think I told you. So remember, it's logarithmic. So each number that it goes down is a factor of 10. And so it's not just a factor of 30 different, it's a factor of 10 to the 30 different. Right? So these are very strong acids. All right, the pH of a very dilute KOH solution. Well, we need to do pH equals 14 minus POH, which is the negative log of 1.6 times 10 to the negative 8. Six. We get a pH of 6.20. What's the matter with that?
Should be above 7, right?
Yeah, this is a strong base. KOH gives us a acidic pH. What the what? What's up with that? Well, it all has to do with the fact that if we're in aqueous solution, then of course the water itself is contributing some OH minus to the solution, and the concentration of H plus in pure water, right, is 1 times 10 to the negative 7 molar, which is 10 times larger than our KOH, right? And so we can't ignore the fact that the water has some H plus in it already. So how do we take this into account? Well, we know from what I just wrote here, right, that the OH concentration is equal to the concentration of let me rewrite this. Well, no, this is good. So the potassium plus, right? The potassium plus, for every KOH that dissociates, we get 1 OH minus and 1 K plus. But also, we get an OH minus for every water that dissociates. And so the concentration of OH minus has to equal the concentration of K plus the concentration of H plus. Right? We only have 1 OH minus concentration, and so it has to be the sum of everything that gives me OH minus, both water and my potassium hydroxide. Now, potassium hydroxide, that concentration is the easy one here, right? Because that's just the concentration we added. That's the 1.6 times 10 to the negative 8. The other two are a bit trickier, but those two have to be related, and they have to be related through KW. And so we can rearrange this. Let me just put in OH minus equals 1.6 times 10 to the negative 8 molar. And because I'm interested in pH, I'm going to leave my H plus as an X, right? And so I'm going to put plus X over here. Now, somebody remind me KW in terms of concentration. What is KW equal to?
Concentration
minus
of OH times concentration of H.
Absolutely. And so I'm going to multiply both sides by the concentration of H plus. If I do that over here, that becomes KW. When I multiply it on this side, instead of H plus, I'm going to write it as X, so that I keep everything the same. And so then we have to do a little bit of math. So we have 1.0 times 10 to the negative 14 equals X squared plus 1.6 times 10 to the negative 8X. All right, we got to do a little bit of quadratic work. Take a minute, see if you remember, negative b plus or minus the square root of 4ac all over 2a. So remember, this is c, a is 1, and this is b. Negative b plus or minus the square root. I got a positive and a negative. Do I need the negative one? No. Can't have negative concentration. The negative one I got was negative 1.1 times 10 to the negative 7 molar. That's no good. Positive one I got 9.2 times 10 to the negative 8 molar. Hopefully you got something like that. And of course, X is our H plus concentration. And so the negative log of that, 9.2 times 10 to the negative 8, is 7.04. While not very basic, it's definitely above 7. And so that makes more sense considering this is a basic solution. Now, the reason I can't just add this 1.6 times 10 to the negative 8 plus 1.0 times 10 to the negative 7, right? If I just want to find the total OH minus concentration. The reason I can't do that is because adding OH minus to water shifts that water equilibrium, right? It's the common ion effect, which we talked about last time. And so we can't just add those two together. We have to see how the addition of that OH minus affects the water equilibrium. Any questions about that one? I think that was the first quadratic we've had to do. All right. Hearing none, I wanted to talk just a little bit about pure water. We talked about purity and its KW gives us a concentration of 1 times 10 to the negative 7 for H plus and for OH minus in pure water. Pure water is real hard to find, right? Not only out in the real world, but even in the laboratory. Pure water is a pretty hard thing to find. And the biggest reason is that CO2 reacts with water to have this equilibrium that forms carbonic acid, H2CO3. That carbonic acid, of course, is going to drop the pH of our water. This has, I don't remember the Ka for carbonic acid, but it's a fairly weak acid, but still it's going to drop the pH a little bit. And so most of the water out there has a pH of something like 6.8. It's something that's really close to 7, but it's not exactly 7. And so, it would be important for us, especially in the last example, it would be important for us to take into account the pH of the water before we added that KOH, if we were really curious about what the pH be. Because the difference of a couple of tenths in a pH, again, remember it's logarithmic, and so that's a pretty big difference in the concentration of H plus and OH minus. All right. So that's really what's happening. There we go. Weak acids and bases. So these conjugate pairs, we talked about that a little bit. And so as the strength of the acid or base goes up, strength the strength of the conjugate goes down. And again, this is based on what we talked about, where K A times KB has to equal KW. And let's just say for argument's sake that my Ka value was 1, right? A Ka value of 1 is where 50% of the stuff goes to products and 50% of it stays as the reactant. And so it's still a relatively weak base, but it gives the Ka value of 1. So if this is 1, and we know this is 1 times 10 to the negative 14, and Kb has to be 1 times 10 to the negative 14. Okay? And so our conjugate base is really, really, really weak relative to that strong acid. Okay? And so the stronger an acid is, the weaker that conjugate base is going to be. So, with our strong acids, things like HCl, HBr, HI, we don't even think of those anions as having any basic strength whatsoever, right? We don't think about, oh, chloride, man, that's a base, because it has almost no base strength whatsoever. Okay. And of course, the opposite is also true. Ammonia is a relatively weak acid. Ammonia is a relatively weak base, but ammonium hydroxide is a pretty strong base, because ammonia is that conjugate acid. So that's the relationship between the strength of an acid or a base and its conjugate. Okay. All right. For a weak acid equilibrium, of course, we know that we could set up our equation, right? HA in equilibrium with H plus and A minus. If this is some initial value, if you think back to chapter 2, I'm pretty sure it was. In chapter 2, no, not chapter 2, it must have been chapter 1. In chapter 1, we talk about different versions of concentration. And we talk about the difference between molarity and formality. Right? Just as a quick reminder, molarity is not what we have treated it like up to this point in your chemical career, right? Molarity is the actual concentration in solution, whereas formality is the amount added. And so for this weak acid, if we have it 1 molar, well, we know it's a weak acid. We know it doesn't dissociate all the way. Is there really 1 molar of acid in there? No, not at all, right? And so when we do these ice tables, we're going to think about this as a formal rather than a molar concentration. And so right now I'm just using F as a placeholder. These start with nothing. We have a minus X here, a plus X, and a plus X, and we get F minus X, whatever our formality is, minus X. And so our Ka is equal to X squared over F minus X. And of course, if you did a lot of these problems in 124 and 124 was recent enough, you don't even have to do the ice table at this point. You can just go straight to this, right? Again, I think I mentioned it on Wednesday. I teach some shortcuts. If that bothers you, please do the ice table. But this is the way that I think about it. And so, this is sort of the quintessential equation for these weak acid kind of problems. Because this doesn't really work if our formality is very, very low concentration. As F and Ka get closer together, and we can't really ignore that minus X, and so we have to worry about other things. Also, as F gets very low, we have to worry about Kw and the H plus that's in our solution. And so, those situations where F is very low, as low as 1 times 10 to the negative 7, we're not making a whole lot of solutions like that, right? Why are we making an acid solution if I want it to have a pH of 7? Just go pour yourself a cup of water. And so those solutions are not practical, and so we won't really do problems with those kind of solutions other than to point out the fallacies with using this equation formula. Okay. And so I'll leave you with this example. Try to have an answer for Monday. The pH of a 0.05 molar solution of trimethyl ammonium chloride, which has a pKa of 9.799. Yeah, I don't think you need to do the quadratic on this one, but I'll let you figure that out. I hope you have a great weekend. Enjoy it. Stay socially distant if all possible. And I will see you on Monday.
Thank you.
Thank you.
Thank you.